So everybody, we're having our next guest on the stage, ENG T Heinapurola from Reforged Studios, senior engineer, and he will be talking about the mobile game engine development. Welcome.
Thank you very much. So welcome to this talk about mobile game engine development at Reforged Studios. I'm going to start off with a short introduction of the company and myself, followed by why we actually started developing a custom engine in the first place and didn't go for Unity or on an Unreal Engine or any other option on the market. But the majority of the talk will actually be about engine development processes and different methods that we use, when developing new stuff on the engine, basically. And I'm going to use a case study, specifically our effects system, to showcase my points. So the company was founded about a year ago, 2015, in Helsinki, Finland, where we have our headquarters. The founders are basically industry veterans, people who have been working on games such as League of Legends, World of Warcraft, Need for Speed, StarCraft 2, a long list of really high-profile titles. And we're focused on mobile games and creating unique worlds and IPs. So my name is ENG T Heinapurola, as already mentioned. I'm basically a game engine enthusiast, in addition to being a gamer enthusiast. I started programming at about 11, started working on engines when I was 14, and still having tons of fun working on engines. My career started in the IT industry originally, where I was for 5 years. But during those 5 years, I did a lot of indie development, developed my own 3D game engines, and released one game on there. But sadly, the game wasn't really a success, so I ended up moving to Bugware Entertainment. Started working initially on Ridge Racer Driftopia, but I was the lead programmer on next car game, Wreckfest. After that, moved to Next Games, initially started working on Compass Point West, but my main purpose for being there was to be the lead programmer on The Walking Dead No Man's Land, the official mobile game for the TV series. So now I'm at Reforged. What I basically do is that I'm responsible for the engine development at the company. So this means that I maintain the vision of the engine, but I also do most of its development. So why did we start developing our own custom engine instead of going for a licensed engine such as Unity or Unreal Engine? Well, we're building an army battler, which means that we have a large number of units on the screen at the same time, large number of effects, and we didn't want to go and use billboards, which is a solution that many other games that need these kinds of requirements on mobile use, because we wanted to have more vivid environment with more complex animations and effects. So this led to very specific rendering requirements. So here's a small thought game. Imagine that the bush here represents us developing our game, which is probably pretty typical for game development. And the task at hand is to actually penetrate this bush with the correct type of tool. So which tool should we choose? Should we take the machete or the Swiss Army knife? Which one would be better? So the Swiss Army knife, which you probably might have already guessed, represents existing engine products, were just too complicated for us to actually modify for our very specific needs. We only needed a couple of tools in the tool set, so we had very specific needs. And neither of those tools, in our case, were really a perfect fit for us. Custom engines, on the other hand, could be simple and efficient. They would be really easy for us to modify to our needs because we have the historical knowledge. We have the people who've been working on the engine. And quite frankly, we only needed the blade for the task. So to quickly summarize, they didn't really fit our requirements. They were just too complicated to take full control of, and we only needed a small set of features on there. So now let's jump into the actual case study of how we develop features in the engine, and let's look at how we did the effect system. So for us, it always starts with a need, like something that is needed by the game team or artists. In this case, it was we already had a particle system. We were able to spawn individual particles and so on, but what we didn't have was a system for more complex effects to take place, such as ones that would contain multiple emitters, dynamic mesh generation, post-processing, whatever. And also we wanted to give the artists the tools to create effects with minimal engineering effort. So then we had these long discussions, and we asked ourselves questions such as, what kind of effects would we actually want to have? How would game code want to control these effects? And how would artists want to create the effects? And so on. And we actually believe in long discussions, in a way. We believe that to get people aligned on a certain feature set, we need to have discussion. Because through discussion, we'll notice all kinds of things that we need to take into account, and things that we might have not thought of originally. And when we're getting people aligned on a certain problem domain, that means that it's easier for us to create an environment of autonomous working, because people know what to expect, basically. So now I'm going to get into the bit more technical parts here. So after asking ourselves these questions, and we knew pretty much what we wanted to do, we needed to start thinking about what was the architecture that we actually needed to implement to support these specific requirements, which were, they needed to be really easy to extend the effect system. It needed to also be really easy to use from game code, and naturally it needed to have really good performance. So before looking into how we fulfilled these in the effect system, I'm going to go through a couple of pillars that are pretty much like under all our engine development. So the first one, strict resource management, then we have lean and clean code, and finally multi-platform development. I'm going to go through each of these in a bit more detail. So first of all, strict resource management basically means that all systems are responsible for managing their own resources. On mobile, it's really important to remember that the amount of memory that the device actually has doesn't necessarily have to do a lot with how much memory you can use. And also, memory access patterns are often a lot more important than actual amount of operations on them. So we need to be really careful with how much memory we allocate and how we use that. Static pools are a method that different systems can use to, if they know how much memory they're going to need during execution. It also supports dynamic allocation overflow. So if you're going to overflow your pool allocations, it's not really the end of the world, at least during development. And that allows for some systems to scale, and then we can report, of course, those allocation overflows and resize the pools. And pools in general, we also support dynamic pools, by the way, can form hierarchies. So it's easier to report how we're using memory on a system-by-system basis. And it minimizes fragmentation as well, because we can create smaller static pools. Then we have object allocators. This is really handy for cases where we need to recycle memory that also needs constructor and destructor logic. And finally, we have well-defined initialization and deinitialization of every system. The second pillar is lean and clean code. So the first thing here is that we try and write what we call orthodox C++. This basically means that we only use C++ features where we actually need to, where it actually provides real value. And we also try to keep our interfaces as simple as possible. And we focus on using C-style interfaces instead of more complex C++ interfaces. And in the right-hand side image here, you can see, for instance, that we have the struct engine entity defined at the very top, and that not defined, but forward declared. And we have a set of functions operating on that object. But we don't need to expose that. So that's one good part of having a C-style interface, because you don't need to expose the internals of the system and of the class or object itself. And the implementation itself is, as mentioned, contained in the CPP files, so modifications to the internals of the system will not propagate to other systems. We also try and implement everything in small interchangeable elements, which basically means that we use small functions, small macros, and so on, instead of large monolithic ones. This improves readability quite a lot. It's important to remember that most of the time when you're implementing new features, you're actually reading code instead of writing it. So readability is a really important thing. And it a lot easier for new programmers to get into existing code and start extending it. And it kind of automatically documents the code as well. Which brings me to my next point, which is self-commenting code. So we try and write code in such a way that it's understandable by just reading the code. So instead of writing tons and tons of documentation and comments, we try and write the code so we don't need that. Of course, it's not always possible, and you do need documentation specifically, but we try and minimize that. And then finally, on this pillar, we have upfront complexity. So a friend actually told me once that, if you see magic in code, it's probably just a really dirty and expensive trick. There's no such thing as magic in code. So we try and be as upfront as we can with complexity in code. So for instance, if you have like a function called getDistanceField, well, it should just get the distance field. It shouldn't calculate the distance field itself. That's a real-life example, actually. So the final pillar is multi-platform development. So we need to target, we target multiple platforms. We have 2 different development platforms, which are Windows and OS X. Then we have Linux for executing code on the server, and we have iOS and Android currently as our main target platforms. So the code needs to work on all of these platforms. We define all of our projects using CMake. So for those of you who are not familiar with CMake, it's basically a system that understands a specific type of scripting language. So we define all our project in that scripting language in a platform-independent manner, and then CMake builds the platform-dependent versions of these for us. We also ported the game as early as possible, and now we're basically just keeping it running and working on all the platforms. And we're actually helped here by continuous integration and automated testing. Automated testing for us currently means that we do unit testing, but we're also planning on a more wider scale integration testing framework. So now I'm going to jump into how the effect system actually works and some of the ways of how we fulfill the architecture requirements. So the front end of the effect system is actually the driver system. So the game code basically only modifies a specific structure, data structure, that it gets when it creates a new effect. And the driver is then executed on this data, and it actually is responsible for updating the effect itself. So only the driver needs to know about the details of how to interface with the effect itself. And here's a super simple example of how this works. So we have the position and rotation in the data, we have the game code modifying the data, and then we have the driver actually rotating and moving the effect. Simple. But how are the effects actually composed? Like, how are they built up? So the effects are basically a collection of components. This is pretty much like a typical entity system. So we use the same framework for defining anything in the scene. So we have, we can have models, we can have lights or anything actually attached to the effect because we use the same system. Each component is basically autonomous. So the component, it defines a system, and instances of that component are allocated or created through that component itself. And updating the effects actually happens on a component by component basis, not effect by effect basis. Components can also link to other components. So most components have at least one dependency. And components can refer to other components by their IDs or by the fact that they belong to the same effect or a specific effect or entity. And component instances are queried from the component systems, as already mentioned, and the IDs are global. So we can basically combine effects to entities in any way we want because we can request other components with their global IDs. So continuing on the example here, we have a very simple example of how we would compose a really simple particle effect. So we would have the transform component in the effect, then we have the particle emitter component, and we have, they're linked. So when we execute the driver, or the game code first modifies the position and rotation of the data it's gotten from the effect system, the driver then updates the position and rotation of the transformation or transform component, and now the particle emitter can actually source the positional information from the transform. So to summarize the architecture here, it's first of all data-driven, so it's really easy for artists to create new effects. We can also create tools really easily on there. The driver system makes the interface really simple, so we only need to expose the properties to the game code that are required for modifying, for linking the game code with the actual effect. And the effects themselves are defined kind of like with a compose and conquer method. This makes extending the system really easy, and also, as mentioned, keeps the interface really simple. So finally, I'm going to talk a bit about one really important property here, which is performance critical. So this is a really performance critical system. For us, this means that we need to be able to, spawn many individual simple effects as opposed to complicated effects. So this means that we need to be able to spawn them really fast. And one way we're doing this, or the way we're doing this, is that we compose templates from the definitions. So when the effect is created for the first time, we actually generate a template from that, and this template contains preloaded mesh information, material information, and pretty much anything you need for creating the effect, or the component, individual components. And basically this makes the creation of the effect into pretty much a memory copy. Naturally, updating and rendering also needs to be super fast. So I'm going to give you one example of how we use data-oriented design, which we use all over the engine, to optimize the particle emitter component more specifically. So here, let's first take a naive implementation that you have a single structure that contains properties such as position, velocity, rotation, and color. And you can have multiple of those particles emitted by the one emitter, and then of course you have many emitters. So basically what a particle operator usually does, it touches only a small set of these individual properties. It doesn't really modify the whole particle. So let's look at how the position of an individual particle would be updated in this naive implementation. So say that a cache line could contain just like one particle. So all the properties in that one particle. And the component now, when updating the particles, it iterates through each of these individual particles. But only the position and velocity are actually touched. So this means that the rotation and color are totally unnecessarily in the cache line. So what we did here is that we organized our data in ways, in the way that we use it. So because we're only accessing a certain amount of properties here, we basically group them, that way. So we can access individual properties separately. So now when we're updating individual properties, we're only touching the positions and velocities because they are consecutive in memory. We're basically having cache lines full of important data. So that actually sums it up. For a quick summary, we chose our engine, we chose to develop a custom engine for reasons of performance and control. We keep a really tight focus on what we actually implement in the engine, which enables us to keep a small team and a nimble one. And I also showed an overview of how the effect system came to be. So here's my Twitter tag, my personal Facebook page, where I usually write small blog kind of posts, and then our company website. Thank you.
Thank you. Any quick questions?
Don't be shy.
Yeah, don't be shy.
Okay, then you see him. You can find him later on if you if you will think of any questions. Thank you again. That was interesting.
Thank you.